Yeah. So now we saw all the fancy stuff. Now we want to see the live version of those fancy stuff. So I think who could be better than the person who cut the cake yesterday, talked about a bite-ready cake. How about a touch-ready? Oh, I'll let David Fuller explain that.
Yeah, let's let David talk about it.
David, please welcome to the stage. David, the floor is all yours.
Oh, thank you. So yesterday I had the pleasure of looking back at the past 25 years of LabVIEW with this amazing cake cutting ceremony. When I was invited out here to cut the cake, I thought, really, I'm going to go all the way to Germany to cut a cake? But then you see this cake, and it's this amazing diagram of 2 LabVIEW control loops. It's truly wonderful. When you look at what LabVIEW has delivered over the past 25 years, and you look at the elements that Norma and Rahman talked about in graphical system design, I want to cover 2 of them in particular, which is leveraging COTS technology, and then first-class integration of I/O and hardware. So this looking back, we've always done that, and when I look forward, I want to qualify this demo by saying this is a very early conceptual prototype. It's as much for internal alignment at NIRND as it is for presentations like this to you guys. This is a 55-inch touch-ready monitor. Yesterday we did the multi-bite cake. This is a multi-touch LabVIEW. So what we have here is a picture of an analog subsystem inside of the zinc chip that Giles introduced earlier. And I want to be able to explore aspects of my zinc chip through a hierarchy of kind of hardware visualization and exploration. So now this is the block diagram of it, and you can certainly see why we like this zinc chip so much. It has 2 ARM A9 processors and an FPGA fabric with a direct connect to it, which is a perfect platform for LabVIEW real-time and LabVIEW FPGA. So I'm going to zoom then further out of this chip, I hope. And you can see it contextualized in a hardware block diagram about how National Instruments might use zinc in, say, one of our FlexRio products. So this is a direct visualization of the hardware, the block diagram schematic, and how the chip is integrated. We think that you need these sorts of views to manage the complexity of systems, where you look at something like a PXI chassis, and you think, well, I'm familiar with this, I know it really well, but within it, you have this complex array of this COTS technology drilling all the way into a hierarchy of the boards and understanding what's going on in your system. I mean, this has first-class integration of hardware visually. I think we've delivered in the past tools like Max, where I think you have I helped build Max, so I can make fun of it. It's a tree representation of this incredibly rich hardware that we've built and that you're using to integrate in your systems. And we think clearly that a graphical representation of software has served us very well for the past 25 years in LabVIEW. We think we need the same sort of first-class visualization of your hardware. One of the very first LabVIEW ads talked about the power through hierarchy, and we delivered that in terms of sub-VI composition, which we were going to show you in terms of LabVIEW's current capabilities. We want to deliver the same capability with hardware itself.
So Max Measurement and Automation Explorer, this is the Max, so to speak, graphical Max inside the LabVIEW environment.
That's
right?
correct. I think the future of LabVIEW is the full convergence in a visual way of the hardware elements of your system with your software overlaid against it. And we're working very hard to fully integrate those 2 products so you have a single environment to completely manage as a console for your system. So what I'm trying to show you now is what we call a top-level system diagram. So in addition to the first-class integration of hardware and this exploration of hardware directly in your environment, we want to create tools that allow you to communicate clearly what's going on from a top-level point of view in your application. And again, each one of these kinds of views that we want you to be able to create to describe your systems has to have some form of hierarchy. So I want to be able to drill into levels of detail about my system. The particular application I'm demonstrating here is an electric car charging system, where I have an electric vehicle that I want to have. I want to be able to prototype with the PXI chassis the behavior of the engine control unit so that I can develop my battery charging algorithm in an efficient way. I then want to be able to monitor the smart grid information, pull it into my charging dock, push it into my car, prototype it, and then put all of that data into a cloud where I can store it and then visualize it from a mobile device. This is a futuristic presentation of possible systems, but these are kinds of systems people are building and deploying today. So the future is now. It's really building these tools so that we can accelerate your productivity to manage this sort of a complex environment. Now I want to transition to another view. This is more of a kind of whiteboard view. We believe that things like functional block diagrams with more formal UML-type methodologies are also important to manage the complexity of your system. Now I'm switching between these views quite a bit. I would say, having worked on the LabVIEW editor for a really long time, one real drawback of a graphical program relative to text is that you have to do your own visual layout and wiring. So that's a productivity hit. We believe that the tools of tomorrow have to have much more sophisticated and advanced auto routing and auto layout capabilities to reduce the productivity burden of that sort of layout. When you look at things like diagram cleanup in LabVIEW today, the core algorithms behind that are some really fancy graph traversal and optimization stuff, but in the end you get basically a very clean LabVIEW diagram. And that lays the foundation for the kinds of auto layout and routing that we're going to do in the future versions of LabVIEW. You'll always have total control of where things are placed and things like that, but we want our automatic algorithms to get it about 90% right.
Hey, David, so just in thinking about how you would interact with this future version of a system design software like LabVIEW, what you're doing here is you're describing your system in a very high level, and then you are able to use individual blocks and the representation of those systems to drill down to every level below it so that you can get all the way from top level all the way down to system functionality at the very low.
That's exactly right.
Okay.
I have a quote up on my board, which we live by quite a bit, and we spend a lot of time talking about. It's called "One man's abstraction is another man's obstruction." What you end up doing is most of the time when you build a black box abstracted system, you're unable to drill down into it and actually see what's going on. And when you're talking about all the kinds of problems that you guys solve, there's no way we as designers of your tools can know in advance everything that you're trying to do. So we've learned over the years some pretty hard lessons that yes, we should abstract things up as high as possible to make it as productive as possible for you, but you really ought to be able to drill all the way down to the pen and write the tightest code that you want when you want to. So I've transitioned over to what I consider to be one of the most fundamental views, and we call it an implementation diagram. And it gives you a very high overview of your system. It's not the communications type diagram I showed at the beginning with the car. This is more of an implementation diagram. It has the same elements, they're just relayed out to show better relationships. Primarily the relationships it shows are, what are my processing elements? And that's our generic term for anything that can run code. And right now is the most fun time in the computer space I've ever been in, with the tablet explosion and the cloud explosion and all these different processors that are available for us to run things on. So I want to be able to show my cloud and show that there's some web services running up there somewhere on somebody's cloud. I've got my PXI controller and that FlexRio I showed you earlier, and then I have my I/O. And then this shows all the relationships, both the physical connectivity as well as where the code is running and what's communicating with what. And when you're talking about these complex systems that we're all building, this is a nice dashboard to start with from that level of detail that I want to see. But as always, you need to be able to drill in. So I have my FlexRio. We talked about Zinc. I want to expand that in place to show, okay, specifically what's running on my Zinc processors and then what's running on my FPGA fabric. And you can see in this particular case, I have a PID algorithm represented in purple that runs as a control element as part of my engine control unit's charging system. So I'm going to go ahead and look at possible implementations of my PID. Now, we talk a lot about this abstract concept of models of computation. And models of computation is a term we stole, with their permission, from the University of California at Berkeley. And this was this idea that you have a design input language that's most appropriate for your engineering problem. So this PID, since it's running on an FPGA, we stole from a VHDL code snippet. Now, I might want to view that same algorithm because I prefer it and I learned it this way using math script or a math notation. Or maybe because I work on the LabVIEW team and I love LabVIEW, I'd prefer to see it as a G diagram. Now, in concept, we've been working very hard for the past years on an intermediate representation for languages, and we call it our data flow intermediate representation. And it's kind of the heart of the data structure that's at the basis of the LabVIEW compiler. And so what we do is we take whatever language you write something in, and we put it into this intermediate code format, and then we can traverse that and generate FPGA code, we can synthesize whatever. In addition to being able to take your code and then target all of these different kinds of devices, we've reverse synthesized out an ability where you can take the code, put it in defer, and then retransform it back into the language of your choice. This isn't shipping, it won't ship for a while, but we can take something like a VHDL algorithm and convert it into a LabVIEW diagram. Now, once I have my LabVIEW diagram, I want to edit it. So this is a presentation about the future 25 years of the direction of LabVIEW, and you can see that in the future, the LabVIEW diagram of today will largely look like the diagram we have, because we think we basically have it right. So one benefit of the COTS technology that we're really excited about is we had this long ago marketing campaign. I think it was something like think it, draw it, do it. And we're finally to the point where the human user interface has caught up with the graphical representations we have in LabVIEW. So I'm going to be able to draw my while loop. I'm going to do a classic random number to strip chart.
That was pretty cool.
Oh.
I just want to,
Did you realize that?
You can clap. It's all right. So I've gone ahead and drawn a random number to strip chart. We think one key takeaway for all of this is LabVIEW is positioned as one of the most touch-ready languages on the planet. If you think about the benefits of touch and a graphical representation and how easily you can directly manipulate it, we're well positioned to dominate the programming landscape for touch-based devices. We see ourselves on tablets and phones and everywhere else as highly amenable to development there. I think if you conceptualize, the benefits of touch to text-based programming languages are almost non-existent. Touch-based keyboards are abysmal relative to a physical keyboard. So we get a lot of lift out of this COTS technology trend, and we plan to leverage it.
Right, so 25 years ago, we had this intuition, graphics and the mouse. That's the future. Today, 25 years later, we have the intuition, graphics and touch is the way to go.
That's absolutely right. I think the invariant in that, whether it's for hardware or software, is that rich graphical visualization of your hardware and your software and the key relationships between them is a fundamentally productive metaphor for designing systems.
So just a caution, this is conceptual. This is in a more of a R&D research environment. It's not shipping, but we'll update you in the future as we go along with this new type of look and feel of LabVIEW.
That's absolutely right. I call this demo my job security. So,
David.
Hey guys.
Great job. Thank you. Okay.
So I
Wrapping
see
up.
our time is really
Yes.
up.
We're gonna go.
We've really stretched. So two quick bullet points maybe. Graphical system design. That's how we started.
Yes.
That's how we would like to finish.
Great.
And I'd like to welcome you to submit for the next year VIP conference our new Graphical System Design Best Paper Award that I would like to introduce here. So we are excited about your papers that you're going to submit when our call for papers will be running. And we will call from today on the Best Paper Award, the Graphical System Design Award.
Thank you, Roman. And by the way, Michael Doms has told me that officially we shall be celebrating with a graphical system design cake at VIP next year.
Oh, okay. Okay, with that, thank you very much for your patience. I think we went a bit beyond our time.
Long today, yeah.
But you'll have a shorter break. But, I mean, what could be more exciting than a touch-ready LabVIEW,
That's right.
So
Okay,
thank you very much.
Thank you.
Done.